So hi everyone, let's get this session started. I'm going to be speaking with you today about some work I've been doing with Robin Blumcode over at Sandia National Labs regarding quantum device characterization. If you have feedback or comments about my talk, please tweet me at Travis_SCH. That would be super useful. So as we start to build large-scale quantum devices, one problem that we're going to run into is that a full and complete characterization of those devices is going to become prohibitively expensive. So consider the problem of state tomography on n qubits. You realize that the number of real numbers you need to use to fully specify that quantum state on n qubits scales exponentially with n. This is awkward because we might not have enough data to fit all of those parameters accurately. Now, lest you think that this is a problem that we're just going to experience in the future, recognize that tomography of continuous variable systems already suffers from this problem. These systems live inside an infinite dimensional Hilbert space, and regardless of which representation you use to think about this quantum state, you would have to specify an infinite number of parameters using only a finite amount of data, and any statistician worth his salt would tell you that that is an extremely, extremely bad idea. So we're faced with the question of how do we find small yet good models? So I've been thinking about this, and a year ago in San Antonio I gave a talk. If you want to know more about that talk, check it out. It's on YouTube. We talked about how we could use model selection techniques in order to solve this problem of finding small models. The exact takeaway of this talk is that we were going to do tomography of continuous variable systems inside a truncated set of subspaces. That is, we were going to formally define a set of models as states that are supported on the span of some number of photons. So we're going to truncate our state to some number of photons. You can think about this pictorially in optical phase space as simply a series of expanding concentric disks. Or if you write down your density matrix in the Fock basis, all we're doing is thinking about adding additional rows and columns to our estimates. Now, with these models, we're going to compare them using log likelihood ratios. Now, this is the formula for the log likelihood ratio. The important thing from this formula is that it involves a maximization over the likelihoods, which means you need to know how to do MLE. We're going to use the log likelihood ratio statistic to compare models to truth. Now you might say, well, why are we doing it, comparing it to truth? Well, because there's a very useful theorem called the Wilkes Theorem that tells us the distribution of this statistic. In particular, the Wilkes Theorem says if your true state, which we're denoting here as rho naught, or the green blob on the left-hand side of the screen, if that true state is contained within your model, then the distribution of this statistic is chi squared sub d squared minus 1. Now, what exactly the chi-squared distribution is kind of unimportant. What is important is that you can compute its expected value. And knowing its expected value when your model contains the truth provides you with a decision rule for determining whether or not your model does when you don't know if your model contains that truth. What do I mean? I mean, you could take some data, you could compute this statistic, and you could compare that value of the statistic to its expected value and use that as a decision rule to add extra photons to your state if the data says that you need to. So now you might say, well, okay, is the talk over? Well, even though the Wilkes theorem is super helpful in predicting the distribution of the statistic, it seems to get it wrong, which was a little bit perplexing. So we did a lot of Monte Carlo, and I'm plotting here on the x-axis the empirical average over 100 identically and independently distributed data sets. And on the y-axis, we're plotting the expected value that the Wilkes theorem says that we should get. This green line here is what we would expect to see if the Wilkes theorem predicted the numerically observed values exactly. These dots are the data that we have. What do you see? These dots are consistently way too high. What this means is that if you wanted to use the Wilkes theorem naively and set a threshold, you would be expecting way too much evidence in order to justify jumping from one Hilbert space dimension to another. This is a little bit awkward because it means that you'd have to take a lot of data in order to arrive at that conclusion. So what we wanted to do is we wanted to ask the question, why? We thought that the Wilkes theorem would work, and yet it seems not to be applicable. So what's going on? Well, we went all the way back to brass tacks and did what any good physicist would do, and that's compute some kind of Taylor series, because it's relatively easy to do, right? Essentially, the Wilkes theorem actually does kind of use a Taylor series expansion, and we're going to take that expansion and kind of muck around with it a little bit and learn something about what's going on. So let's compute the Taylor series out to second order. So that's why we have this funny looking notation here is actually how you would write a Taylor series of density matrices when you represent them as vectors in Hilbert-Schmidt space. So this is kind of like the complex vector space analog of doing one-dimensional Taylor series that we're all familiar with. By definition, the 0th order term vanishes. We assume the 1st order term vanishes, and we're left with this. Now, what the heck is this expression? What is it telling us? Well, this quantity in the middle, the double partial derivatives, that is simply the Hessian of the log likelihood, which is also known in the statistics community as the observed information. This kind of matrix element type thing, that is a vector formed by taking the difference between the true state and our estimates, is what we're calling a fluctuation tensor. So pictorially, what you should be thinking about is we have some distribution of estimates, which I'm going to show here as kind of these yellow shapes. And then you also have contours of the log likelihood as defined by its Hessian, which I'm plotting here in orange. And the log likelihood ratio statistic depends upon the interplay of these two. So without boundaries, we recover the Wilkes prediction. You can follow a pretty straightforward series of analyses in which you argue that in the absence of boundaries, MLE is not biased. You can also invoke asymptotic efficiency of MLEs to saturate the classical Kramer-Rao bound. And you derive that the expected value of lambda is d squared minus 1, exactly what the Wilkes theorem predicts. So where does this go wrong in state tomography? Briefly, with boundaries, fluctuations become distorted. Quantum states have the positivity constraint. That's manifest in the fact that we have a block sphere to describe qubits. Because of these boundaries, this fluctuation tensor has to respect them, which means that all of the nice properties that we had previously, like unbiasedness of the estimator, asymptotic efficiency, those no longer apply. So we can kind of start the first two lines of an analysis, but then we're like, well, where do we go from there? Well, if you beat on this long enough and think about it, you realize that a good thing to do would be to rescale the observed information by that fluctuation tensor. Like, okay, what does this mean, Travis? It just means we're going to invoke the cyclic property of the trace to rewrite that expression in this nice symmetric Hermitian form. Now, in what follows, I'm going to present some data from actual numerics, and so I want to set this up with an example. So if we did qubit tomography and the Wilkes theorem applied, so we kind of forget about the fact that the block sphere has a surface, then this tensor is the identity. We execute a change of basis to go to the basis of matrix units. These numbers are going to tell us how much individual density matrix units contribute to the log likelihood ratio statistic. The trace simply extracts out these diagonal matrix elements. So we do the same and reshape them into a 2x2 grid. We're going to compute a whole bunch of these grids for different true states and for different model dimensions and see if we can't figure out what's going on with the Wilkes theorem breaking down. So let's do qubit tomography on the most benign state we could ever imagine, the vacuum state. What do we see? Well, remember, the Wilkes theorem predicts that the grid of numbers should look like this. This is the grid that we actually see. Some agreement with the off diagonals, but the on diagonals don't. What happens if you go to other model dimensions? So d equals 2, d equals 3. Remember, darker equals higher absolute value. D equals 4, d equals 10. If the Wilkes theorem were true, every single one of these off diagonal blocks would be dark. But they're not. But this L-shaped kind of thing is dark, right? Is there some way that we could build a model that could explain the expected value just kind of using these shapes? Yes. In fact, you do what's the most obvious thing. You say, okay, clearly the most important thing is what we call these coherent matrix elements. That is, they are matrix elements in the estimate that are coherent with the subspace on which the true state has support and between that subspace and the kernel of the truth. So that's what the L represents. And then there's also a spectral degree of freedom. Now, you can think about this sort of geometrically in the sense that if you have an estimate, you can unitarily perturb that estimate in some directions and they won't see the boundary. That's the L. The estimates can also fluctuate locally normal to the boundary, and those are spectral degrees of freedom. So you can write down a formula, modulo some Monte Carlo that I'm not going to talk about in this talk, and we can compute the expected value, or rather, we can estimate it. So how well does this model do? Well, let's take a look at the plot I showed earlier and superimpose our data shown here in blue. It is very clear that there's kind of two things going on. That is, we have the Wilkes theorem, it's consistently too high, it's wrong, doesn't apply. We have our model, which does much better. It's much closer to this green line. Now you might step back and say, well, Travis, what about these guys, right? These dots up here in the upper right, finite sample effects, and you can talk to me more about that offline. So where does all of this leave us? I think there are three key takeaways. The first is that we shouldn't be using the Wilkes theorem or related ideas like the Akaike information criterion for solving some model selection problems, namely when there are boundaries that we have to reason about. The second is that we managed to find a building block for a replacement, this notion of coherent L's or crosses or other such things, and spectral fluctuations. And that does much better in estimating the expected value. The awkward thing is that it says that different parameters in your density matrix are going to have different contributions. And what's more, that these contributions are actually very strongly dependent upon the sample size that you're using. Now, from a 30,000 foot view, what we're doing is we're trying to build a new tool for model selection in quantum state tomography. As we build more and more complex quantum devices in whatever architecture you like, we're going to grapple with the fact that the states that these devices are producing only have so much structure, and we need to model that structure very well. Thank you for your kind attention. Thanks everyone for checking out that video of my March meeting talk. Admittedly, 10 minutes is not a lot of time to describe many details behind one's research. So if you're curious about the ideas and concepts presented in this video, I have two videos that I would encourage you to go check out. The first is from a talk that I gave last month at Squint 2016, which is about half an hour long, and the other is a talk that I gave in December 2015 to update my dissertation committee, which is about an hour long. Both go into a lot more detail about the research presented in this video, and I would encourage you to check them out if you're curious. Now, as always, if you have feedback or ideas for how these videos can be improved, feel free to leave a comment below. Thanks.